Hi students. This is an example of how to design a V-belt drive. This is example 7.2 from your textbook. Design a V-belt drive that has the input sheave on the shaft of an electric motor, normal torque, rated at 50 horsepower at 1160 RPMs, full load speed. The drive is to lift a bucket elevator and a potash plant that is going to be used 12 hours a day at approximately 675 RPMs. Okay, so what we're given here is we're going to have an electric motor that's going to be driving this belt drive system at 50 horsepower. It's going to be turning at 1160 RPMs. That is the speed of that motor. We're supposed to reduce that down to 675 RPMs for our drive. And these types of belt drive problems, this is a full-blown belt drive problem, and it's like 12 steps. There's a lot of processes to them, so there's going to be several movies to get through this one. But the first step is to find the design power. Okay, and how we do that is we need to consult this table 7.1. I have a posting in Blackboard that has all of these belt drive design slides in a single file for your reference. So I put them in one file so you can see them. So the first step, this find design power, we're going to consult table 7.1. What we're going to look at here is we've got a normal torque AC motor, which is going to be driving our system, and then we're going to be operating that system 12 hours a day. So that's in this column here. And then now we need to select this column here. So the type of machine, smooth loading, agitators, conveyors, stuff like that. Light shock loading would be generators. Moderate shock loading, those are bucket elevators. So this is where we want to be. So our number for design factor is going to be 1.3. We're going to read it off of this. Okay, so what we have to do is we take that 1.3 and then we multiply it by our horsepower rating, and that means our design power is 65 horsepower. So essentially what that means is we're going to design this system, we're designing a system for 65 horsepower is what we're going to do, based on the type of machine this is. Our next step is going to be to select the belt sections. There are several sizes of V-belt drives, and then based on these rated powers, we need to pick the proper section of the V-belt drive. In this textbook, we talk about 3 Vs, 5 Vs, and 8 Vs. Okay, so to do the belt selection, we're going to look at this figure here, 7.13. What we have is we have a logarithmic scale on the x-axis of the design power. That's the one we just calculated, and the speed of the faster shaft, which we know is 1160 RPMs. So we're going to find where 65 on the x-axis, which is between 60 and 70, and we're going to follow that up to see where it intersects with 1160. So I'm getting that right about here, right in this area, right about there. Okay, so what that tells me is we are in the zone here that is firmly the zone for a 5V belt. Okay, so that is our selection. We're going to choose a 5V belt based on this. Okay, so our next step is to compute the nominal velocity ratio for this reducer drive. Okay, so really if our RPMs are coming in at 1160 RPMs, and we need to reduce that down to 675. Our velocity ratio is 1.72. That's equation 7.4. That's the drive that we need to end up with. We need to reduce our input speed down to 675. Okay, so next we're going to find the nominal diameter of the driver sheaves. Okay, so these sheaves for our pulleys, the pulley sheaves, the same, we use those terms interchangeably. They're available in sizes, and what we try to do is find the proper size. Okay, so there is a note in your textbook for step 4 that says find the nominal diameter of the driver's sheave. And there's a note in your textbook on page 245 at the beginning of the chapter. And it reads that linear speed of the belt is usually 2,500 to 6,500 feet per minute, which results in relatively low tensile forces on the belt. If you get lower speeds, the tension on the belt becomes too large for the typical cross-section, and then slipping may occur between the sides of the belt and the sheave. And then at higher speeds, dynamic effects such as centrifugal forces, belt whip, and vibration reduce the effectiveness of the drive and its life. Therefore, a speed of 4,000 feet per minute is generally ideal. Okay, so when we design these V-belt drives, what we're going to try to do is shoot for a velocity, a belt velocity of 4,000 feet per minute. Okay, so we do that. We'll go over to 7.3, and then this equation 7.3, it relates our diameters of the belts, the sheaves. These are actually the pitch diameters of the sheaves, to the velocity of the belt. And we solve that for diameter 1, which is the diameter of the smaller sheave, and we get 2v divided by n, which is the speed. So if I was to do all unit conversions here, we have 4,000 feet per minute. That's the velocity, our target velocity for our belt. And we're going to convert, we multiply it by this, we divide it by the speed, which is 1,160 revolutions per minute. And then we need to convert our units here. We know there's 2 pi radians in a revolution, and then 12 inches per feet. So that gives us our starting diameter of 13.17 inches. What I would like to do is pick this up in the next movie. Thank you.